In aerospace-grade design, resolving competing mechanical, electrical, and thermal requirements relies on weeks of cross-functional meetings. Departments spend months colliding over dimensional constraints. The true bottleneck lies in the administrative artifacts. Engineers manually compile design failure mode and effects analysis spreadsheets and construct separate parameter diagrams across isolated teams. The AutoGain ecosystem, specifically the Magnus Genesis architecture, replaces this manual administrative friction with a computational solution. The architecture reduces cycle times by condensing 6-week definition phases into hours, executing a single mathematical generation called a design epoch. Generating CAD geometry is a solved problem. The actual barrier to scaling mechatronic systems is calculating the underlying reliability logic that dictates what that geometry must be. This rendering displays the completed Magnus kernel V6.5 gimbal system. It is a 2-axis stabilized assembly engineered to manage a 0.91 kilogram payload within a strict 80 millimeter physical envelope. This specific geometry exists to survive a highly aggressive environmental profile, including 5G dynamic loads and the environmental stressors outlined in MIL STD 810H. This blueprint illustrates the underlying engineering logic generated simultaneously with the 3D model. Notice the extreme density of the interface hierarchy table. The architecture autonomously maps the mechanical, thermal, and electrical flow across 13 highly specific component connection links. The primary advantage of this pipeline is the front-loading of design for reliability logic. This happens before a single physical prototype is committed to manufacturing. By automating risk profiles and fault trees at this stage, the architecture embeds design for reliability logic directly into the project's earliest design baseline. To understand the pipeline's logic, we isolate one critical path. Here, we evaluate the system's calculations for bearing protection and reliability. The pipeline begins by computationally assigning explicitly stated functions to every item listed in the bill of materials. The peak bearing seat receives the strict assignment to mitigate brinelling, while the chronometer 30 bearing is assigned to support rotation. This diagram outlines the auto-generated FMEA tables. The architecture tests these functional assignments against potential catastrophic operational failures. In this instance, the system flags a specific mechanical failure mode, true brinelling of the bearing races. It assigns this risk a priority number of 80. The algorithm traces the direct cause, peak shock loads exceeding Hertzian contact stress limits, straight down to the root cause, insufficient preload control via crush ring spacers. Because it identified the root cause mathematically, the system autonomously mandates specific prevention controls to resolve it. It dictates the physical implementation of a crush ring spacer to prevent the failure, and it mandates torque ripple analysis as a detection control. The algorithm identifies the risk, redesigns the local geometry, and then alters the downstream manufacturing test plan to ensure the risk is actively detected on the assembly line. This parameter diagram reveals the robust design engine at work. It balances competing physics constraints against uncontrollable real-world variables for the chronometer 30 bearing. We begin with the signal inputs driving the bearing's function. The architecture requires a defined rotational torque input alongside a 50 to 150 Newton axial preload force. These signals must survive the noise factors. The geometry is forced to withstand uncontrollable ambient temperatures ranging from -40 to 125 degrees Celsius and bearing race surface roughness variance. To counter this noise, the architecture dictates rigid control parameters. It locks the required material hardness between 60 and 62 HRC and mandates a C2 internal radial clearance. The diagram then splits the output response. It contrasts the ideal target, a dynamic load ratio under 0.5, against the calculated error mode of increased acoustic noise exceeding 45 decibels. These parameters are highly interdependent. Changing the lubricant viscosity grade to counter thermal noise will immediately impact the friction torque output. The P-diagram resolves these competing mechanical constraints mathematically, ensuring that target reliability is immune to field variation. If a core stakeholder requirement changes mid-project, what happens to these massive, interconnected data tables? Consider a hypothetical scenario. The specified system payload mass is unexpectedly increased from 0.91 kilograms to 1.5 kilograms. In a traditional workflow, the engineering team must manually reset all localized stress analyses and rewrite the FMEA spreadsheets to account for the new load limits. The Magnus Genesis architecture simply executes a new design epoch. It instantly recalculates the entire P diagram, immediately requiring a higher peak modulus or chronometer hardness to compensate for the added mass. The Magnus architecture maintains robustness as a continuous, dynamically computed state. This vertical flowchart illustrates the traceability chain, the final phase of the generated manifest. The chart links top-level requirements, like SR101 bearing protection, directly downward to specific variation analyses, such as the tests for true brinelling. The ultimate destination of this traceability chain is the generation of verified Python boundary representation scripts. The mathematical limits established in the parameter diagrams translate automatically into the Boolean operations and dimensional variables of the Python geometry. The digital thread is unbroken. Every CAD fillet and tolerance is backed by synthesized risk analysis. The autonomous synthesis pipeline shifts the day-to-day reality of the reliability and systems engineer. Manual spreadsheet population and the tedious tracking of noise factors are completely removed from the workflow. Engineers operate as high-level constraint architects, verifying the logic of the synthesized system. Time is reallocated to pushing fully documented designs directly into validation and production testing strategies. Competitive advantage in mechatronics now belongs to those who achieve 99.7% reliability at epoch 0 before a single part